Hello, everybody. Thanks, Ryan, for organizing this. This was awesome. So I'm Igor. I work at Facebook in a team that develops RocksDB. And
I'm Ian. I work for infrastructure at Facebook.
And we're going to switch gears a little bit. So far, we have been hearing a lot of awesome talks about a lot of systems that run on hundreds or thousands of machines. And we are going to talk about single node performance, which is also interesting, trust me. So just by show of hands, let me get a sense of the room. How many of you have heard of RocksDB or are familiar with RocksDB? Wow. Wow. How many of you have worked with spatial databases before? Cool. Approximately the same. So let me start with introducing RocksDB. RocksDB is a single node key value store, meaning we expose a normal key value API. You can put the key with the value, and then you can get the key and hopefully get the same value you just recently put into RocksDB. We keep the keys sorted, so you can do range scans, which is useful if you're building database systems. Then you can have secondary indexes on that, and so on. RocksDB is optimized for fast storage, meaning we run it most heavily on Flash and RAM. It's developed by Facebook. We started as a fork of LevelDB, and we still share some code base with LevelDB, but we made a lot of improvements, especially for optimizing it for Flash and RAM workload, and also optimizing it for server, high-end server devices. RocksDB is open source. We open sourced it last November, and we are very happy that we got a lot of attention from the open source community. I'm also very happy that you guys have at least heard about it. It's widely deployed inside Facebook. A lot of services inside Facebook use it. On various different workloads, various different storage devices, even some spinning disks, even though we are not optimized for spinning disks. But we have also seen some adoption from outside companies. For example, LinkedIn is heavily using RocksDB. Then there are some small startups that deploy their data on RocksDB. And we've even seen Dropbox using RocksDB for some kind of search features. Anyhow, Yin and I were hanging out in Boston this summer, working with Ryan. And what Ryan said, I need something to store spatial data. I need a database that will store, as a first use case, map data, vector map data. So roads, buildings, lakes, rivers, stuff like that, so we can render that map data efficiently. And then the question is, why are we not using off-the-shelf databases? So that's a valid question, and they are very general in purpose. You can load spatial data in it and then have some SQL queries on top of it. You can think of PostGIS as an extension of Postgres for Geo-spatial database. I think even MySQL has some Geo features built into it. And that's all very good. But our experimental project was to find out how much better can we get with a spatial database built especially for map data. And hopefully in the future we'll extend it for some other use cases. But we want to focus for highly optimizing this one particular use case and see how much better can we get. But there are also other reasons why we decided we want to build this spatial database on top of RocksDB, and two of them very simple ones, and we have in-house support. We have a team of 5 to 6 people working on this full time, and if something breaks, we have somebody to call. Right? If PostGIS breaks, we don't have anybody inside of Facebook who's familiar with PostGIS, and so we are a bit more hesitant working with PostGIS than we are with RocksDB. Also, we have operational know-how. As I said before, there's a lot of different services at Facebook that store data inside of RocksDB. And we depend a lot of our stuff on RocksDB. So we are very confident we know how to run it, we know how to scale it, and we know who to call when it goes down. So these are some of our reasonings why we decided to experimentally build something that can very fast serve spatial data and especially map data. So, okay, now we have our ground rules. We want to build something that's very fast for map data. So let's think, what are the unique characteristics of a map data workload? First thing is that we found very quickly is the data fits in memory, which is mind-blowing. So if you take the entire planet and take all the roads, all the buildings, and everything you have, that thing fits in memory on one node. And I was like, wow, this is crazy. And this also enforced our thinking that RocksDB might work better in this case because RocksDB is specially optimized for in-memory workloads. Another thing is, if you want to design highly optimized storage, you want to optimize it for reads, not writes, because when you basically how we use this is we do a some giant import. We get a plain text XML format of the entire planet database. We do some kind of lengthy import process, and once we're done with import, we only serve reads. So we can trade off this load time. We don't care if it's 1 or 2 days, if we can get more and more performance out of it. And we can also trade off space. Even in some extra space that we do trade off, we can still achieve if we can achieve very high read rate, it makes sense. And even if it doesn't fit on one single machine, it's easily sharded. But for this use case, we got about 70 gigabytes of a database that we can easily store it on one single node in memory cache. So let's talk about, oops, you should have warned me that something is behind me. I hope I didn't pour water on something bad. Anyhow, let's go to the spatial database schema. So here's what we did. Here's what general purpose databases usually do. You take your spatial databases, spatial data, load it into spatial database, and then on the rendering time, when you want to render your map, you take, let's say you have a tile, you say, I want all the buildings that are in those tiles. I want all the roads that are in those tiles. And then you determine if you're, let's say, rendering for zoom level 6, you take a tile, you take all the features that exist in those tiles, and then you filter out all the buildings, you filter out all the roads, because you're not going to show them on zoom level 6. So that means on the read time, you're doing a lot of processing. And what we decided to do, since we can trade off our load time, we decided to move that processing in the pre-processing state. So instead of doing it in the read time, we will do it on the import time. So what we do in the import time, we take features one by one, and then we find a building. This feature is a building, let's say this hotel in Boston. And then what we say, we are only going to show this building in zoom level 17. What we have then is we have multiple different spatial indexes, each spatial index for different zoom level, and then we insert this building only in a spatial index for zoom level 17. If you load a road that's not very important, we might show it in zoom level 17, 15, and 16, but not in all the lower zoom levels. So we only insert it into those spatial indexes. If we load a country border or some giant lake that you want to show on, even if user zooms out the map fully, in that case, we will insert that particular feature in all grid indexes. So here we show how we trade off load time. So we do some pre-processing, and then how we trade off space. So instead of one spatial index, we have multiple spatial indexes. Actually, one spatial index for each zoom level, which will add some extra space, but when you go to read, your read is for a particular zoom level. Your user says, I want to render this map on zoom level 10. You will go exactly to one spatial index and load exactly the data that you need to render. You will not load buildings if you don't want to render buildings, because you'll go exactly to that spatial index that you want to render. So here, rectangles, you can think of them as tables. We actually use RocksDB's feature that's called column families, but you can just think of them as tables. And we have a data heap table, and data heap just maps unique ID to the data, where data is some kind of geometric representation of the object. And then we also have spatial indexes, each one spatial index for each zoom level. And there, we map a quad key to a list of IDs. And quad key is a unique way of indexing a tile in a one giant grid index. And the good property of quad key, and the reason why we use quad key, is that it achieves data locality. So tiles that are close to each other are also geographically close to each other, are also close to each other in the database. And this is useful even if you're on database in memory. So the way we do this is when we have a grid index, we just split the entire space we want to index into equal tiles. And there are two things that define each index. One thing is bounding box, which says this is the 2D space I want to index. And another one is granularity. And you can think of indexes for zoom level 6 need to have a bit lower granularity, so less number of tiles than indexes for zoom level 17. And then for indexes at zoom level 17, we configure this number of this granularity a bit higher. So we have more and more tiles that index our data. And this we specify a list of indexes when we create a database. So now we create the database, we want to insert some data in it. And when we insert data, we take 3 parameters. One parameter is the actual data. And the actual data is just serialized blob, so just binary format. And what it represents is 2 things. One thing is geometric representation of an object. So is it the line, point, polygon, the latitudes, longitudes of each point in the polygon. And also there's a feature set. And for feature set, you can just think of it as a key value pairs describing the object. So for this particular hotel, it would probably be the fact that this is hotel, the fact how many stories does it have, the name of the hotel, and so on. For a road, it might be a short nickname of a road, name of the road, and stuff like that. For example, for a country, it may be the name of the country. And the fact that this is a country border and the fact that this is the road is also something that we store in the data. Then we have a bounding box, which is just a minimum rectangle that encompasses your geographic object. So we index data by bounding boxes, by rectangles. And in the end, we take a list of grid indexes. So as I said before, if you take a building, you insert it only into zoom level 17, and if you take a country border, you insert it into all grid indexes. So this is what we take as an API input to our spatial database. When you do a query takes a bounding box, which is a space that the user needs rendered as a map, and it takes a grid index. So if you want to render a feature at zoom level 17, you will query against that index, only for index 17, and you will get this pre-processed data back, returned back to you. And what you do there is pretty simple. We take the bounding box and then find all the tiles that intersect that bounding box, which is just a simple procedure, and get all the data that's mapped to those tiles. And this is what we have this is what we store in RocksDB. With that, I will hand over to Yin, who will talk how we are actually using this spatial database, or how we're experimenting with this spatial database.
So as a test case, we will try to serve OpenStreetMap through this new feature. How many of you have heard about OpenStreetMaps before? Okay, good size of people. So for those of you who are not familiar with it, it is the largest open source map community out there. Its map data comes from 3 sources. One is out of copyright, like government maps. Another is through commercial donation of mapping companies. And then crowdsourcing is also a major component of OpenStreetMaps. People try to map their own roads by GPS data or by satellite image. And as Igor mentioned, it's not a huge amount of data. It's not growing like super fast, but it's growing roughly linearly every year, adding about 100 gigabytes to the database every year. So by now, it's roughly 550 gigabytes of data. Not a huge amount, but still, we need some optimization to make sure it fits in memory and serves our needs. The format of the data consists of 3 different types of nodes, what they call node, way, and relation. Node is mostly like an intersection or point of interest. And then way could be an actual road or could be a border. And then relation is a composition of nodes and ways to represent certain geometries. Could be a building polygon, it could be a lake, a boundary, or could be other shapes. They use tags to annotate these 3 data types to add some property to it. To annotate, for example, if a way is one-way road or two-way, or if it's a freeway or local road. And this is also in the XML style data. Why so much interest in open source maps? First of all, hey, it's free, right? If you use Google Map or any other map, eventually they will charge you something. And also another major benefit of it is that it allows people to actually update and correct maps. I've heard complaints from Microsoft and other companies who use commercial maps that they know something is wrong, but they couldn't fix it because of the copyright limitation. And also it helps for customization. Sometimes if you need your own rendering style, you need some own special routing objective, then you can do it yourself. And also it's good for special purpose maps. Sometimes we want to build some heat maps, then we can also use OpenStreetMaps. For example, here in this graph, we show that if you use taxi traces, you can automatically find certain problems in your map and try to correct them. And then in terms of how to import OpenStreetMap to RocksDB, at a very high level, this is what Igor mentioned earlier. We try to analyze the tags of all those 3 data types and try to see what are the contents of it. And then we try to insert them into different indices of this room level hierarchy to make sure it serves our needs. For example, country border and coastlines, it goes to the lowest room level. And then like freeway, we go to the middle. And then if you zoom to the highest level, then you see local roads and building. But they don't have to be at the low room level to save space. A lot of engineering work went into this importing pipeline, and we try to optimize speed as well as the spatial efficiency as the final result. So after all this optimization, it takes roughly 10 hours to import this whole planet OSM data, and the final size, as Igor mentioned, is roughly 70 gigabytes, which fits in memory of our commercial machines. And then, as a benefit of our grid index compared to, for example, PostGIS or other SQL-based databases, we have a very simple design. We have only two tables. One stores all those data, and one stores all the indices. And then for each query, if we want to render a tile, we just need two queries. First, we get all those data features of that particular tile, and then another query to fetch the actual data, the actual geometry to actually render the tile. And then it's very easy to customization because of a simple design. So in terms of performance, I'll hand it back to Igor.
So I heard the slide is not, the presentation is not complete with the performance. So I want to give you some performance numbers, but don't take this too much seriously, because they depend very much on the style you use. You know, if you decide you want to show every building that you can on Zoom Level 6, of course, those queries might be a bit harder and heavier on our server. But on x-axis here, we show you zoom levels. So you can see zoom level 6, zoom level 8, 11, 14, and 17. And on the y-axis, we show QPS, so numbers of queries per second we were able to achieve. This is measured on a Sandy Bridge architecture. I think 16 core machines, if somebody keeps track. And what we see here, and that for zoom level 6, we were able to achieve about 50 QPS, for zoom level 8, 200 QPS. And the reason for that is that average query for zoom level 6 returned 5,000 features, where for zoom level 17, where we were able to achieve 35,000 QPS, the average query returned only 2 features. If you take random sample of Earth, there's not much happening there. But this is a good problem to have, because, for example, for zoom level 6, the data doesn't change often. These are the country borders, so country borders don't change often unless you're from Balkan states. So we can cache most of that. We can cache, there's only 4,000 tiles at zoom level 6, so we can cache all of them, pre-render all of them, and just serve them from our CDNs. Where for zoom level 17, when there are a lot of tiles, we might not want to cache all of them because there's a lot of storage space. We achieve a lot of good throughput and good performance when querying. So with that, I would like to ask you to check it all out. It's all open source, except the importing pipeline. But I think we also plan to make this open source at some point. So the spatial database, the whole indexing part, everything is open source, lives on our GitHub, part of RocksDB. So if you downloaded RocksDB, you also downloaded this. I don't know if you know that. And I also give you some pointers to our webpage, blog, and then Twitter. Thank you. Thank you for listening. And if you have any questions. For each, do these tiles line up? We hope that they line up, but I think they don't currently. I mean, we are trying to make them line up because we have a tile, and it's a integer, like x, y, and zoom is the way we index the tile. But in the worst case, it's 4, right? In the worst case, it's 4 if you overlap 4 rectangles. But we hope to align that so it matches up and it's only 1. No, you definitely can. So you definitely can. Like, you can give us arbitrary bounding boxes. You can say, give me all of this on zoom level 17, just be slower. But what we are planning to do is when we render a map, right, we want to render only this particular tile, and that we plan to align that tile with our internal representation. But yeah, you can create whatever you want for whatever spatial index you want. That's an interesting question. R trees are interesting when you try to implement on top of a LSM architecture that is RocksDB. It's not easy. R trees are mostly optimized for kind of like B tree variants, and they optimize heavily for seeks. So there are 2 ways why they might be good. We didn't experiment with them. We just want to build a simple and performance solution, and it seems to work. It performs finely. With R trees, it might be more work to figure out how they actually work, how to implement them on top of LSM tree, and then are they actually suitable for in-memory workloads versus them as in the first place being designed for seeks. for optimizing seeks instead of in memory. Okay, thank you guys.